We're going to do some more related rates problems. Now, in the last video, we did 3 problems, so we're on problem 4 right now. It says a certain bacteria cell has a spherical shape. If the volume of the cell is increasing at a rate of 4 cubic micrometers per day, at what rate is the radius increasing when the radius is 2 micrometers? And we give a hint here that the volume of a sphere is 4/3 pi r cubed. Okay, now the first step, remember, in solving these related rates problems is to draw a picture of the situation or a diagram. So we've drawn a picture here of this bacteria cell. And the second step is to define variables as functions of time. So we have V and R. So remember, this cell is increasing in volume each day. And so the radius is going to be increasing as well. So we think of the V here as being V of t, and the R as being R of t. And so we have this equation now that relates our variables. So actually, we've done the first 3 steps of our strategy. We've drawn a picture, we defined variables, and we found an equation that relates our variables. Now, remember, the next step is to take a derivative of both sides with respect to t. Okay, look at this equation. Take the derivative of both sides with respect to t, and let's see what happens. Now, the derivative of v is just going to be dv dt. The derivative over here, well, 4/3 pi, that's just a constant. And we have 4/3 pi r cubed. The way to take the derivative is we're going to bring the 3 out front. Now, when the 3 comes out front, the 3 here is going to cancel this 3, and we're just going to be left with 4 pi. So when you take the derivative, the 3 comes out, and we end up with 4 pi r squared, but then times dr dt because of the chain rule, or implicit differentiation is what we're really doing here. So we have dv dt equals 4 pi r squared dr dt. Now, the question was, if the volume of the cell is increasing at a rate of 4 cubic micrometers per day. So that's one of the things that we know. What we know is dV dt, the rate of change of the volume, is 4, or 4 cubic micrometers per day. At what rate is the radius increasing when the radius is 2 micrometers? So we're going to plug these things in. We're going to plug in 4 for dV dt, and we're going to plug in 2 for r. And the one thing that we have left is dr dt, and that's the exact thing that we're looking for. At what rate is the radius increasing when the radius is 2 micrometers? So let's plug things in. We have 4 equals, now 2 squared is 4, times 4 is 16. So we have 16 pi times dr dt. So dr dt is going to be 4 divided by 16 pi. Okay, dr dt equals 4 divided by 16 pi, which is really 1 over 4 pi. Now, if you use a calculator, you can see this is really 0.0796, and this would be micrometers per day. Okay, that's the rate of change. So this is rounded to 4 decimal places here. That's the rate of change of the radius. Okay, 0.0796 micrometers per day. That's how fast the radius is changing when the radius is 2. Okay, the next problem says, for a certain type of tree, the height of the tree in inches is related to the radius of its trunk by this formula. So in other words, if you know what the radius of the trunk of the tree is, that'll give you an idea of what the height of the tree is, right? In fact, this is a model for this a particular kind of tree, but you can plug in the radius r, and that will give you the height of the tree. Okay, suppose that the radius increases at a rate of 3/4 inches per year. How fast is the height of the tree changing when the radius is 8 inches? So we've drawn a picture here. My tree looks not so great here. It looks like a lollipop or something. But we have a tree, and this tree has a radius for its trunk, and it has a height of the tree. And usually we give the diagram to kind of help us come up with a formula, but actually we were just given the formula here that relates our 2 variables. And so again, h and r are thought of as being functions of time. And so we have h equals 180 r to the 2/3 power. So just like before, we're going to take the derivative of both sides with respect to t. And what we're going to get on the left-hand side is really just dh dt. On the right-hand side, when we take the derivative of this, the 2/3 comes out front. Now, 2/3 times 180 is really 120. Times r to the, well, we have to lower this power by 1. That would be negative 1/3, right? 2/3 minus 1, or 2/3 minus 3/3 would be negative 1/3. But then times the dr dt. Okay, so now we're going to plug in what we know, and that will help us find what we don't know. So what do we know? Well, we know that the radius is increasing at a rate of 3/4 inches per year. So in other words, dr dt, the rate of change of the radius, is 3/4 or 3/4 inches per year. I'm not putting the units here, but it's really 3/4 inches per year. How fast is the height changing when the radius is 8 inches? So we want to know when r is 8, what is going to be dh dt? How fast is the height changing? So we're going to go back to this formula and plug in what we know. So dH dt is going to equal 120 times r to the negative 1/3, but our r is 8, times the dr dt, which is 3/4. Okay, so let's plug things in here. We have 120 times, well, this is really 1 over 8 to the positive 1/3, or the cube root of 8, times 3/4. Now the cube root of 8 is just 2. And 120 times 1/2 then would be 60, and we have 60 times 3/4, and 60 times 3/4 would be 45. So what does that number 45 mean? Well, that's 45 inches per year. That's the rate of change of the height when the r is 8. When the radius is 8, the height of the tree is increasing at a rate of 45 inches per year. Okay, let's do another problem. It says a girl flies a kite at a height of 300 feet with the wind carrying the kite horizontally away from her at a rate of 10 feet per second. How fast must she let out the string when the direct distance from the kite to her is 500 feet? And we're going to assume that the string is taut. In other words, there's no slack in the string. So I've drawn a picture of the situation. We have a girl down here on the ground with this kite being flown at a height of 300 feet. Now that height is not changing. Okay, the kite is going to be carried horizontally away from her, but this height of the kite is going to be 300 feet the entire time. And the wind is carrying the kite away from her horizontally at a rate of 10 feet per second. So notice we have this triangle here. It's really a right triangle. This height is 300. We'll call this distance A here, but notice that A is really changing. In fact, the rate of change of A is going to be 10 feet per second. A is increasing, right? This distance right here, this horizontal distance between the girl and the kite is increasing. And also this distance from her directly to the kite is also changing. It's increasing as the kite moves away from her. So we're going to call it C. Now, eventually, we're going to plug in 500 for C, right? Because the question is, how fast must she let out the string when the direct distance from the kite to her is 500 feet? So the kite's going to have, she's going to have to let out the string because the kite's moving away from her. But the question is, how fast? In other words, how fast is C increasing? Okay, what is the rate of change of C? So what is the relationship then between our variables? Now notice I could have called them A, B, and C, but this B here, this height, is not changing. So I'm just calling it 300. Well, we have the Pythagorean theorem that says that A squared plus B squared equals C squared. But again, our B is just 300. So we have A squared plus 300 squared equals C squared. Or in other words, A squared plus, well, 90,000 equals C squared. Okay, so here's our equation that relates our variables. Now we're going to take the derivative of our equation with respect to t, with respect to time. So we'll take the derivative of both sides. That's a t there. Okay, and so what is the derivative of the 90,000? Well, of course, that's just going to be 0. What's the derivative of a squared? Well, that will be 2a times dA dt. So that's the left-hand side. The right-hand side, what's the derivative of c squared? The derivative of c squared is going to be 2c times dc dt. Now, by the way, the 2's can cancel out on each side here, divide out a 2 from both sides. So now let's plug in what we know. Okay, what do we know? Well, we know that c is going to be 500 because we're trying to find how fast is c increasing when c is 500. So we know this c is 500. You can also use the Pythagorean theorem to solve for a. So we have a squared plus 300 squared equals 500 squared. It turns out it will be 400 though, because 300 squared plus 400 squared will equal 500 squared. So you can do that and check it if you want, but that's what a is going to end up being, is 400. Now we also know that dA dt, the rate of change of a, how fast a is changing, this horizontal distance, is that 10 feet per second. Okay, so dA dt is 10. So these are really 500 feet, 400 feet, and this is 10 feet per second. So now let's plug them in to this equation right here. Okay, so let's plug in our A. Well, we have 400 for A. We have the dA dt, which is 10, 400 times 10, equals C, which is 500, times dC dt, and that's the thing we're trying to find, dC dt. Okay, so notice this is really 4,000 equals 500 times dC dt. Well, if we divide both sides by 500 now, we'll see that dC dt is 4,000 divided by 500, which turns out is just 8. So I rigged up the numbers to be just nice here. It was really nice that the A ended up being exactly 400 as opposed to some crazy decimal, some crazy square root. And it also worked out really nicely that the dC dt was just a number 8. Now, what does the number 8 mean? Well, is that 8 feet? Well, that's 8 feet per second. Okay, that's how fast she's going to have to let out the string. Now, the kite is moving horizontally away from her at a rate of 10 feet per second, but how fast C is increasing, how fast she's going to have to let that kite through her fingers here, is at a rate of 8 feet per second. All right, number 7 says a large spherical balloon is inflated with helium at a rate of 100 pi cubic feet per minute, or that's about 314 cubic feet per minute. How fast is the balloon's radius increasing at the instant the radius is 5 feet? And then also, how fast is the surface area increasing at that instant? Now, we're given the formula for the volume of a sphere and also the surface area of a sphere. And notice this is actually quite similar to our problem that we did with the bacteria cell, but there we weren't asking this additional question about surface area. So I've drawn the picture of the balloon here, and we've labeled our variables R and V. We're also going to have another variable later for S, for surface area. But again, this is really a V of t and an R of t. And we have an equation here that relates our variables. Okay, so we're going to take the derivative of both sides of this equation with respect to time. So the derivative on the left side equals the derivative on the right-hand side. And again, this is going to remind you of the bacteria cell one. The left side will just be dV dt. On the right-hand side, we bring the 3 out front. We're going to get 4 pi r squared times dr dt. Okay, so here's our equation. Now we have to plug in what we know. Well, what we know is that we want to find how fast the balloon's radius is increasing at the instant the radius is 5 feet. So we're going to plug in. So when we say no here, we're going to plug in r equals 5, or 5 feet. We also know that the balloon is inflated with helium at a rate of 100 pi cubic feet per minute. So in other words, the volume is increasing, so the dV dt, at a rate of 100 pi cubic feet per minute. So dV dt, the rate of change of the volume, is 100 pi cubic feet per minute. So we'll plug these in here. dV dt is 100 pi equals 4 pi times r squared, but r is 5, times dr dt. Well, that's our unknown. That's how fast the radius is increasing, the rate of change of the radius, and that's what we want to find out. Well, so notice we have 100 pi equals, well, 5 squared is 25 times 4 is 100, so the right-hand side is also just 100 pi times dr dt. And if we divide both sides by 100 pi, you can see that dr dt is just 1. Well, what does that mean, dr dt is 1? That's the rate of change of the radius. Now, our units here were in feet and in minutes, so that would really be 1 foot per minute. That's how fast the radius of that balloon is increasing, at a rate of 1 foot per minute when the radius is 5 feet. Okay, so that's our answer to the first question, is 1 foot per minute. Now, the second question says, how fast is the balloon's surface area increasing at that instant? And we have a formula here for the surface area. Okay, S is equal to 4 pi r squared. And now we're going to take the derivative. Let me go back to the blue here. Take the derivative of both sides of this with respect to t. And the derivative on the left-hand side is just going to be ds dt. The derivative on the right-hand side, well, the derivative of 4 pi r squared, we bring the 2 out front. We get 8 pi r to the 1, but then times dr dt. Okay, now what is it that we know? Well, we're still considering the same instant when the radius is 5. Okay, radius is 5 feet. But then what is dr dt? We're trying to find ds dt, but we have r and dr dt. Well, notice we're not given dr dt in the initial problem, we weren't given that, but actually that's what we just found. Okay, in the first part of the problem, we found that dr dt was 1 foot per minute. So now we're going to use what we found in the first question, the first part of the problem, right here. So this will just be 1 or 1 foot per minute. So when we plug this into this formula, ds dt is equal to 8 pi times r, but r is 5, times dr dt, but dr dt is just 1. So notice the right-hand side is just 40 pi, which I believe is 125.7. And I just checked it, and actually it is 125.7. Now, what would the units on this be? This is ds dt. How fast is the area increasing? Well, this would be square feet per minute. Okay, square feet per minute. We're using minutes and feet. So this is how fast the area is increasing. The surface area is increasing at the instant that the radius is 5 feet. And again, what's a little bit unique about this problem is that we actually used our solution to the first part, that we found that dr dt, and that helped us in the second part of the problem when we were trying to find ds dt, because we needed to know dr dt at that instant that r is 5. Okay, let's look at number 8. So it says an airliner passes over an airport at noon, traveling 500 miles per hour due west. So this airplane goes over this airport at noon, and it's traveling 500 miles due west. And at 1 p.m., so an hour later, another airplane passes over the same airport at the same elevation, traveling due north at 550 miles per hour. Assuming both planes maintain their equal elevations, how fast is the distance between them changing at 2:30 p.m.? Okay, so we've drawn a picture here, and here's my airplanes. By the way, don't make fun of my airplanes. I know they're bad. But I had a brother growing up. I mean, I still have a brother, older brother. He was amazing at art stuff, and he could just draw these elaborate things. And we went to a baseball game, Detroit Tigers baseball game. He like drew the entire stadium. We came back home, and my mom would always put up his pictures on the refrigerator, and I don't ever remember her ever putting a picture of mine on the refrigerator. And I was wondering at the time, why? But I look back, and it's just my art was awful. It was terrible. Okay, anyways, I don't know where I'm going with this. But okay, so we have this airplane. That first one goes over due west, 500 miles an hour. We have the next one going north at 550 miles an hour at 1 o'clock. So the question is, how fast is this distance between them increasing at 2:30 p.m.? Okay, so notice we have this triangle here. And in fact, it's really a right triangle because this is traveling directly north. This is traveling directly west. So we have a right triangle. And all of these distances are actually changing. There's none of them that are staying fixed. Okay, so we're going to call this distance A, and A is increasing, right? We'll call this distance B is increasing, and we'll call this distance C here, and C is increasing. So clearly, we have an equation that relates our variables, just A squared plus B squared equals C squared. Okay, and then we're going to take the derivative with respect to t of both sides. And what do we get? So by the way, just think about this. Okay, how fast is that distance between these two planes increasing? Okay, how could we figure this out? Imagine trying to do this without calculus, right? How would we figure this out, right? Okay, well, let's do this here. It's actually not going to be too bad of a problem. So let's take the derivative. We get 2a dA dt plus 2b dB dt equals 2c times dC dt. And by the way, we can divide everything by 2. So actually all these 2's can really cancel out if you divide both sides by 2. But I'll just leave them in there. So now notice we have really 6 things. A, dA dt, B, dB dt, and C, dC dt. Okay, now we're going to plug in some things though. So we have to figure out what is A, what is B, and what is C. So first of all, what is A? Well, remember, this plane travels over this airport at noon, and it's going 500 miles this way. And we're talking about at 2:30, so 2.5 hours later. What is A going to be? Well, if this is traveling 500 miles an hour for 2.5 hours, well, if we double 500, we get 1,000. Get another half of it, would be another 250. Wouldn't this be 1,250 miles away from the airport, right? That plane. So A, so one of the things that we know is that A is going to be 1,250. Also, we know dA dt. What's dA dt? Well, what's the rate of change of A? How fast is A changing? Well, it's just 500 miles per hour, right? So this is, again, 1250. This would be miles. This would be 500 miles per hour. Whenever you're talking about a derivative, you're talking about a rate, right? This is 500 miles per hour. Okay, now what about B? Well, remember, this one goes over the airport at 1 o'clock, and then we're wondering at 2:30, how far has it gone? So basically an hour and a half later, we need to multiply 550 times 1.5, right? 1.5 hours. And if we do that, 550 times 1.5, that'll end up being 550 plus 275. Let's see, what is that? 825? Yes, I believe that's right. So that'll be 825 miles. So notice the A is going to be 1,250. The B is going to be 825. And the C, oh, by the way, what is dB dt? Well, dB dt, how fast is B increasing? Well, it's 550 miles per hour. Okay, now the question is, what's dC dt? That's the question. But we can now figure out what C is. In fact, C should be the square root of a squared plus b squared, right? Because a squared plus b squared equals c squared. So C should be the square root of 1250 squared plus 825 squared. Okay, and I'm not sure if that turns out to be a nice number. Let me check. Okay, I just checked, and this is approximately equal to 1,497.70658 dot dot dot. Okay, so it's a little less than 1,500 miles. That's how far these are apart. 1,497.7 miles approximately. Now, you could leave it like this, the exact number, when you're plugging it in for C, so that way we don't get any round off error. In fact, that might be the best way to go. But let's start plugging things in now. So here is what we know, these things. And here's our equation that we're going to plug things into. So let's go ahead and do it. So we have 2 times 1250, that's A, times dA dt, which is 500, plus 2 times B, which is 825, times B dB dt, which is 550, equals 2 times C. Now I'm going to leave C kind of a blank here, but that's what this 1,497.7, that's where that's going to go, times dC dt. Okay, and that's what we're trying to find, is what is dC dt. So we have everything except the dC dt. Now the left-hand side, what that simplifies to be is 2,157,500. And that equals this 2 times C. Now for C, you could put in the square root. In fact, that might be the better idea, is to plug this in the way it is. So that way you don't have any round off error. Or we could use this, but we're going to use enough decimal places that the round off's not going to be bad. We're going to have 1,497.70658 times dC dt. And if you work this out, dC dt would equal this divided by this, and that ends up being approximately 720.3. Now, what does that mean? That's 720.3 miles per hour. That's how fast the planes are moving relative to each other. That's how fast this C is increasing at 2:30 p.m. And for our last problem, we have this one, number 9. A balloon is rising vertically above a level, straight road at a constant rate of 1 foot per second. Just when the balloon is 65 feet above the ground, a bicycle moving at a constant rate of 17 feet per second passes under it. How fast is the distance, S of t, between the bicycle and the balloon increasing 3 seconds later? Okay, so this bicyclist, I assume there's a person on the bicycle that just says a bicycle, but anyways, this bicycle passes underneath the balloon at a certain moment, and at that moment, the balloon is up here at a height of 65 feet. So this actually is not a bad drawing. It looks like a balloon, or looks like it's going to impregnate something, actually. But so it's 65 feet above the ground, but it's rising at a rate of 1 foot per second. And this bicycle is moving this way at a rate of 17 feet per second. So the question is, 3 seconds later, so by the way, the balloon would then be at a height of 68 feet. Is that right? Because it's 65 feet when it's right underneath it. 3 seconds later, it's going 1 foot per second. It'd be at a height of 68 feet. And also 3 seconds later, the bicycle will be way over here. How far over? Well, 3 times 17, I believe, is 51. So the bicycle will be over here at 51 feet. From there, this height will be 68 feet. And the question is the distance between the bicycle and the balloon. How fast will that distance be increasing at that moment? So they're calling this S, or S of t, this distance. And notice we do have a right triangle here. So we're going to use the Pythagorean theorem again. We'll call this distance A, we'll call this distance B, and what we're going to get is A squared plus B squared equals S squared. So that's our equation, a squared plus b squared equals s squared. And notice all of these three things are changing, A, B, and S. So I'm not plugging in 68 here or 51 here, not plugging anything in for S. All of these distances are changing. So we're going to leave it at all three of those lengths here as variables. So we're going to take the derivative of both sides with respect to t. Now, again, all these problems are very similar, right? We've had kind of this same strategy for solving all these problems. It's amazing that this one strategy works in all these different cases. So what we're going to get is 2a times dA dt plus 2b times dB dt equals 2s times ds dt. Now let's actually just cancel the 2's here. We can divide both sides of the equation by 2. I didn't do that in the last problem with the airplanes, but you can do that. I'll get rid of some 2's here. So what is it that we know in this situation? Well, remember, we're not going to plug in 65 for b. Why are we not plugging in 65 for b? Because, well, that's not what b is going to be 3 seconds later. Initially, this height is 65, but after 3 seconds, since this is going up at a rate of 1 foot per second, this will be at a height of 68. So we're going to put in 68 for b, 68 feet. And a will be 3 times 17, right, which is 51. A will be 51 feet. Okay, now what else do we know from this equation? Well, we know dA dt is 17, right? dA dt is 17. That's how fast A is increasing, the rate of change of A. It's 17 feet per second. dB dt, what's dB dt? Well, dB dt is just 1. That's the rate of change of B. That's how quickly that's increasing, right? The balloon is rising vertically above this road at a constant rate of 1 foot per second. Okay, and now the question is, what's ds dt? Oh, we also have s. Now, what is s? Well, s is going to be the square root of b squared plus a squared. So s is actually going to be the square root of 51 squared plus 68 squared. But if you work this out, I actually rigged this up so that it would end up being a nice number. If you work this out, it actually is just 85. Okay, it's actually 85 exactly. So let's plug things in. We have 51, so that's our A, times dA dt, which is 17, plus, this is a plus here, plus B, which is 68, times dB dt, which is 1, equals 85 times ds dt. Now, the left-hand side ends up being 935, and that equals 85 times ds dt. So ds dt is going to be 935 divided by 85, which turns out, so I really rigged this one up to be nice, it turns out it's just 11. Now, what does that number 11 mean? Well, that's ds dt. That's the rate of change of s. How fast is s changing? Well, that would be 11 feet per second. And that's our final answer. So notice all these problems, we used a similar strategy to solve these problems of drawing a picture, defining variables, finding an equation that relates those variables, taking the derivative of that equation with respect to t, and then plugging in the things that we don't that we know and solving for the thing that we don't know, the thing that we're trying to find. I think it's an amazingly beautiful strategy that works in so many different problems in so many different contexts, and I hope that you can see that these related rates problems are really interesting problems and they're really useful to know how to do these. And you can also see the usefulness of calculus to doing these problems.